Hi everyone, this is Integration 101 from the Design Lights Consortium's 2024 Controls Summit. This is the agenda that I'll cover. What are NLC and LLC? Why should anyone care about NLC HVAC integration? Common challenges for integration projects, types of HVAC, types of integration, and case studies. We'll start with the basics. What exactly are NLC and LLC? The term Networked Lighting Control, or NLC, can mean different things to different people. For the Design Lights Consortium, it means a combination of sensors, network interfaces, and controllers that affect lighting changes in luminaires, retrofit kits, or lamps. These devices may communicate with each other using a wired protocol such as DALI 2, or a wireless protocol such as Bluetooth. When sensors for occupancy control and daylight harvest are on board every fixture in a network lighting control system, that's called Luminaire Level Lighting Control, or LLLC. That is good for spaces of all sizes and especially good for smaller buildings. The DLC considers LLLC to be one kind of network lighting control, or subset. Some network lighting control systems are connected to the internet, while some are not. Others have an occasional internet connection through an operator's mobile device. Next, we'll explore some of the reasons why we at the DLC think NLC HVAC integration is important. You've probably heard about building automation as the wave of the future. Integrating lighting controls with HVAC controls is an obvious place to start for the lighting industry to move more into the world of building automation. HVAC is a good place to start because it uses a lot of energy. Today's commercial buildings use more than half of their energy for HVAC and about 10% for lighting. An LED retrofit can save half of that lighting load, or sometimes less if the old lights being replaced are already LED. When a lighting retrofit includes network lighting controls, that saves about half of the remaining new lighting load. But that happens rarely because uncontrolled LED lights are cheap and NLC systems seem expensive when they only save a few percent of the whole building load. Now here's the fun part. An NLC system powers, networks, and distributes occupancy sensors evenly throughout an entire building. In sustainable buildings, signals from those occupancy sensors can inform the HVAC controls to relax the temperature set points by a few degrees in areas that happen to be unoccupied. Some buildings can also reduce the ventilation rate for additional energy savings. This is called occupied standby mode. Signals from a network lighting control system to an HVAC system enable occupied standby mode by telling the HVAC system when each part of the building is occupied or unoccupied. The total combined savings from lighting plus HVAC with occupied standby mode can be over 20% of the whole building energy load. In some of the most recent building code revisions, occupied standby mode is required in parts of a building where occupancy sensing is required for the lights. In order to use occupied standby mode, some buildings get occupancy signals from the network lighting controls. When this integration is well planned and executed, it can save time and money compared to the alternative, which is for the HVAC system, to have its own independent network of occupancy sensors. This is a substantial waste of hardware, effort, and maintenance that could be avoided if the HVAC system worked together with the lighting system. Our analysis showed that whether the local electricity prices are high, as in Connecticut, or low, as in Arizona, NLC HVAC incentives for integration are cost-effective for utilities, as shown on the right in blue, in more types of large buildings than NLC alone, shown in yellow. On the horizontal axis, any benefit-cost ratios larger than 1 are cost-effective, and BCRs higher than 3 are truly outstanding bargains. An incentive program for network lighting controls with HVAC integration can serve more utility customers in more types of buildings with deeper energy savings compared to NLC alone. Now granted, electric utilities focus on electric load. In some places, space heating has mainly been powered by gas and oil, so reducing the heating load has not been a high priority. But now, with new heat pumps, aiming for decarbonization and electrification reductions in heating load are becoming much more important to electric utilities. Now that we have shown that NLC HVAC integration can save energy cost-effectively, let's take a look at why it doesn't already happen more often. we'll see some of the challenges that can make NLC HVAC integration difficult and keep it from saving much energy. These challenges create an opportunity for energy efficiency programs that can encourage people to make a little extra effort to save energy by integrating the NLC and HVAC systems. Support from efficiency programs could make it easier to meet the new building codes and also save more energy with minor lighting retrofits that do not trigger code. In some commercial buildings, activities run like clockwork. The facility manager knows exactly when each space needs to be conditioned, and they always schedule the HVAC system to run when it's needed and not when it's not. In a building like that, occupied standby mode will not save enough energy to be worth the trouble. But other buildings are less predictable, especially post-COVID. With many workers now on hybrid work-from-home programs, plus high commercial vacancy rates, spaces in some buildings might be occupied or not at any hour of the day or night or week. Another challenge for NLC HVAC integration is how well the HVAC control zones line up with the lighting control zones. Loosely speaking, an HVAC control zone is a space where the temperature is set by a single thermostat, and a lighting control zone is a space where all the luminaires do the same thing at the same time. The floor plan is divided into 3 large rooms. There are 2 thermostats in the building. One controls the temperature in rooms A and B, and the other controls the temperature in room C. There are 3 lighting control zones, 1 for each room. In general, lighting zones tend to be smaller than HVAC zones. In this example, the HVAC zone and the lighting zones line up well, so the lighting system can provide appropriate occupancy signals to the HVAC system by combining occupancy signals for rooms A and B. But in other buildings, the HVAC zones and the lighting zones do not align, so it's not easy to get signals from the lighting system that are appropriate to control the HVAC system. In this case, the HVAC zones are the same as before, but the lighting zones are set up with a daylight zone at the perimeter and an interior zone for the rest of the space. In order to feed occupancy signals to the HVAC system, the systems integrator will need to map every lighting occupancy sensor and then send individual signals from every sensor to the HVAC system. Zones need to align their boundaries and also their names. A rose by any other name in software is difficult to put into groups of roses. Each person who configures an NLC system or an HVAC system gives each space and each control zone a name, which is usually whatever name they feel like. The room names in the lighting software may be completely different from how the exact same rooms are named in the HVAC software. Data ontology, naming conventions, data tags, and semantic requirements are some of the words that you'll see related to this challenge. Back to our floor plan for how different naming conventions in HVAC versus lighting can complicate things. In this example, the rooms are named A, B, and C in the HVAC system software, but they're named West, Northeast, and Southeast in the lighting system software. This example is only 3 rooms, so it's not really that complicated. But imagine if you had dozens or hundreds of rooms with completely different names in the HVAC system versus the lighting system. Integration would be manageable but time-consuming. These are 4 somewhat related but distinct efforts to standardize naming conventions about what to call the different stuff in a building in North America. If everybody on a project can agree at the start of the project on one of these naming conventions to use, then people can communicate more successfully because they're all speaking the same language. Speaking of different words, here are 3 terms about building automation. A BAS is a building automation system. This is the hardware used to automate a building and to connect different building systems together. A BMS is a building management system, which is the software running on the BAS hardware. This enables users to monitor and control multiple building systems such as HVAC, lighting, fire alarms, security cameras, access, etc. with one coordinated schedule in one software program. A BEMS is a building energy management system that is extra software with extra functions such as inventory management and energy monitoring. If a building has any of these things, it is more likely to be a good candidate for NLC HVAC integration. Our next challenge is again how things are described. The Construction Specifications Institute, or CSI, is a nonprofit dedicated to improving the communication of construction information to improve project delivery processes. They develop and maintain a standardized outline so that construction specifications can all be organized with the same general headings. For instance, lighting is always specified in Division 26 under Electrical, and HVAC is always specified in Division 23. In other words, lighting folks never look at Division 23 because that belongs to HVAC contractors, and HVAC folks never look at Division 26 because that belongs to electricians. Therefore, there's a special section called Division 25 dedicated to all the ways that multiple building systems need to work together. Division 25 is rarely used, but when it is used, it's very helpful for successful integration. If you ever hear something about CSI Div 25, you'll know that's the special section of a construction specification that describes integration between multiple building systems. Here are examples of some of the things that can be specified in Division 25 to get different people working together so their different systems will work together. Exactly which software parameters will be shared between systems? Can the BAS control and change any lighting parameters or only read them without changing? And what technical details are available in the sequence of operations document to say exactly how each function should happen? Next topic is latency, the art of managing lateness. This describes the time it takes for data in a network to go from one place to another. With network controls, there is always a delay between a request for something, such as a person pushing a light switch to get light, and the response, such as the lights coming on. That happens later. When there's a noticeable gap in time, people complain. With an old-fashioned light switch and incandescent light bulb, latency is very low, almost instantaneous. When you add an NLC system, the latency gets a bit longer, but manufacturers usually keep the delays short enough so you rarely notice. However, if they try to send a signal from a light switch through a BMS and then over Ethernet to an NLC and then to a luminaire, the delay might be multiple seconds and people would complain. Here's a quick example. Occupant expectations for latency tend to be around 200 milliseconds for a switch or sensor to activate a light. That looks a little something like this. For HVAC, response times can be seconds or even minutes, and system architecture can have a direct influence on this. This doesn't translate well to lighting. Here's what it looks like with a latency of only 2 seconds. The majority of occupants would be unhappy with this. We're not going to get into many details about different HVAC systems, but I wanted to mention a few things that are especially relevant to NLC HVAC integration. If you get involved in some integration projects, you'll probably hear the term VAV, or Variable Air Volume System. This describes the kind of HVAC system where the fan can run faster or slower depending on how much ventilation is needed. The term VAV can also apply to a box called a VAV box that attaches to an air duct and has controllable louvers that let out more air or less air according to the control signal for that space. One VAV system typically will have many VAV boxes. VAV systems support occupied standby mode well because they can dial back the ventilation rate in any space that is empty and increase it when a space is occupied. The alternative to a VAV system is called constant air volume, or CAV. That means that the fans can turn on or off, but they cannot change speed. CAV systems are common in older buildings, but less likely to show up in newer buildings. With a CAV system, occupied standby mode might save a little energy, but not very much unless you do an expensive upgrade to replace all of the fan motors with variable speed motors and add VAV boxes to all of the duct outlets. The type of NLC HVAC integration depends on the size of the building. NLC HVAC integration rarely happens, but it's feasible now in many large buildings and sometimes actually happens in large buildings that have digital building management systems. In a large building with a building management system, the BAS can manage multiple building systems, including HVAC, lighting, and others. Sometimes the BMS can schedule and monitor all the different systems from one central dashboard. communication between systems usually occurs with the BACnet communication protocol. Setting all this up requires customized software programs for each building, so it's common in very large buildings and campuses, but the customized software can get too expensive to be justified in smaller buildings. Still, NLC HVAC integration sometimes occurs in smaller buildings that do not have a BMS. Today in small buildings, it's usually done with old-fashioned analog technology called dry contact, which is an analog switch that opens or closes for vacancy or occupancy. In this method, a wire sends a signal from the NLC to each thermostat or controller that can dial back the ventilation and temperature conditioning when a space is vacant. A new method that is in development is to use an NLC system based on a Bluetooth mesh network to add a control node at the thermostat so the Bluetooth-enabled thermostat can read occupancy signals from within the lighting Bluetooth mesh network. Chris Walgamot at NIA is working on a project to demonstrate this idea, and the Bluetooth Special Interest Group is developing a new thermostat profile to match the recent Bluetooth NLC standard for mesh networks in lighting. Another approach for small buildings is to reduce the cost and complexity of installing and programming a building automation system to make them more accessible for more buildings. Several HVAC controls and BAS manufacturers have released products aimed at this market segment, and 2 papers from national labs were presented on this topic at the ACEEE Summer Study in August. When Bluetooth NLC gets a thermostat profile, that will bring NLC HVAC integration into the 21st century for small and medium-sized buildings. In the meantime, dry contact provides a tried-and-true path to integration that's available today. When lighting is direct install today, giving away free LED retrofits to reach underserved communities, or postpone upgrades in the electric transmission and distribution systems, NLC HVAC integration or even plain NLC is never included. But soon, as integration becomes more feasible in smaller buildings, direct install programs for small businesses could provide an LLC lighting system with the friendly phone app, plus a Bluetooth connection with the thermostat to support occupied standby mode to deliver serious energy savings to small and medium-sized buildings. And now, let's look at a few case studies to see how some of these topics all fit together. I want you to see that despite the challenges, NLC HVAC integration does in fact sometimes happen successfully today. Menlo Business Park is a Class A office park in Silicon Valley with office, lab, and warehouse space for small and medium-sized pharmaceutical and biotech companies. It's a campus of 12 buildings with 500,000 square feet of space. Enlightened retrofitted all the lights with an LLC network lighting control system, providing occupancy and temperature data from every luminaire to the BMS. All that data is analyzed and used to fine-tune the HVAC system dramatically based on occupancy. A third-party energy audit found a reduction in electricity bills of 30% from the retrofit. They used $500,000 of incentives, which is conveniently an even $1 per square foot of the space. This is a good example of the kind of large-scale multi-building successful integration projects that Ron Bernstein, one of our summit speakers, works on for large buildings and portfolios of buildings, where the cost of customized integration software is amortized over a large space. Here's another example of a large retrofitted space consisting of 10 Kaiser Healthcare buildings in San Diego. Wilden made extensive upgrades, including replacing the lights with NLC, integrating the controls, and also replacing all the HVAC fan motors with variable speed drives. These numbers are for all the retrofit upgrades combined. The $3 million retrofit project would have paid back in 2.5 years without incentives, and efficiency incentives brought the payback down to 1.8 years. Here's a case study by the DOE Integrated Lighting Campaign in a smaller building, an Air Force Base industrial area of 21,000 square feet plus 5,000 square feet of office. The LLC system, again from Enlightened, had a 12-year simple payback by itself. When it was integrated with the HVAC system, that reduced the payback to only 7.3 years. Granted, both of those payback numbers are high for anyone except the government, which emphasizes the point that in order to do more integrations in medium-sized buildings like this, We need more standardized plug-and-play solutions that do not require customized project-specific software. DLC has recently updated our page of links to NLC case studies, and we'll be adding a whole section at some point for NLC HVAC integration case studies like these. Here's a recap of what I've presented. 1. Luminaire level lighting controls are one kind of network lighting control. 2. NLC HVAC integration can save a lot more money than NLC alone. 3. There are some challenges to successful integration, which makes this area ripe for encouragement and support by energy efficiency programs. 4. Variable air volume HVAC systems work well for occupied standby mode, constant air volume not so much. 5. Integration can be done in buildings of any size, and new developments could make it a lot easier soon in small buildings. And 6. People often complete integration projects successfully, especially in large buildings and campuses.